So let me fix the code. So I'm going to distribute the iteration amongst the threads. So all the threads seem to be working on the entire array. So let me have each thread work on different parts of the array. So how do I do that? Well, you can write this code on your own, so you can have a look at it offline. Essentially, all I'm doing is that setting a from and a to, a start and a end for every thread based on its thread ID. Right? So I divide the whole array size by the number of threads. So that is like dividing 1 billion by 4. And then I allocate one region to each thread, which ranges from array size by numt into tid up to array size by numt into tid plus 1 minus 1. These are some intricate plus 1s and minus 1s, which I'm sure you'll be able to figure out on your own. Okay. For the last thread, I have to be a little careful because the total space may not be equally divisible into 4 parts. So I have to be careful about what I do with the last region. Right. So this is just a special case to handle that. And then I have just printed this. This is again something you should be very, very careful about. When you're trying to gauge the performance of your code, never have printf statements inside the timed regions. Okay, they cause excessive overheads. Okay, so I ran this code now, and actually when I collected the time, I did not execute the print statement. Okay, I did not time the print statement. So that's just for convenience that I've put this code together. Alright, so what do I see? Well, now I see that thread 0 is actually working on the region from 0 to 250 million, about that number, right? And so on, right? So the array has been equally divided among the 4 threads, and I get the sum of the array elements as something, and the total time taken is 4 seconds. Right, so at least I got the time down. So one part of the code is fixed. Okay, I start to see some use of threads, but obviously I still have a problem. What's the problem? That the sum is not coming out correctly, right? And we know why that is the case. So we need to fix that next. Let's just compare this time we are getting. Yeah, so as we said, right, it's roughly about 1/4 the time of the sequential code, right? How do I fix the other problem? So there is a construct called hash pragma OMP critical. What it does is, the region immediately after hash pragma OMP critical, I can, if I have multiple statements, I can put it in curly braces like I've done before, right? If it's a single statement, I can just write it without any curly braces. And what hash pragma OMP critical does is that it ensures that this particular region, the hash pragma OMP critical region, it's called a critical section. This region is only executed by one thread at a time. 2 threads cannot be executing instructions inside this region at the same point in time. Okay, so it ensures that this entire region is atomic, that no other thread can be executing these instructions while one thread is executing these instructions. That means that when I'm trying to do the sum plus equal to ai, right, if thread 0 is executing the instructions load ai into R1, right, does a load of sum into R2, and then it says add R2 R1, so add R1 into R2, and finally store R2 back into sum, right? So while one thread, let's say thread 0 is executing these instructions, thread 1 cannot execute any of these instructions. It cannot enter this section. So if thread 1 during its execution encounters this statement, obviously this is the first statement it will encounter, this particular load, right? It will not enter this region, it will not execute these instructions. So there are ways of ensuring that, right? Using locks and semaphores and other mechanisms, right? So we'll get into those later. But essentially the system can ensure for you that the other thread will not even reach this instruction. Okay, it will get blocked before this instruction. It will wait there. So, I mean, one simple way of doing this is that you keep a separate variable which is a lock, right? And whenever any thread enters this region, it updates this lock to 1, saying that I have locked this region. And then if any other thread wants to start executing this region, it first checks this lock, whether it's 1 or 0, right? If it finds it to be 1, it will keep waiting until it doesn't become 0. Okay? and thread 0, once it finishes execution, it is going to reset this back to 0. So if any thread is waiting, it will again check the value of lock. Now it finds it to be 0, so it's going to change it to 1 and start executing. Right? There's one obvious problem you should see with this solution that I gave you for lock. Right? What is that? That I have used lock as a mechanism to ensure that only one thread executes this region at a time. But what about lock itself? That's a shared variable, and it's possible that two threads may update it together. How can that happen? So thread 0 tries to check whether it's 0 or not. So thread 1 also tries to check whether it's 0 or not. So both of them fetch into the register the value of this lock. Both of them get 0. Both of them change it to 1, put it back. They both think they have the lock. Both of them proceed and execute the code. So this is not the way locks are implemented. Okay. So there's generally an instruction called test and set. So it's a hardware instruction. So what it does is that if you say test and set x, right, what it will do is it will fetch the value of x and simultaneously update it to 1. It will update it to 1 and fetch the value just before it is updated to 1 back for the programmer. Right, so let's say I have a location x. So what will test and set do? So let's say the current value over here is some alpha, right? So when I call test and set x, immediately after test and set x, it's going to return me the value alpha, right? And it's going to set this location to 1. It's going to replace alpha with 1. It's going to store the value 1 at location x. What does the programmer have? The programmer has the value of alpha, the value that was there just before I wrote 1 to this location. And this is done atomically. So how can you use this to implement a lock? So the way you use this is, now that lock we were talking about, right? What you do is you say test and set lock. What will this do? This will set lock to 1 and it will return you the previous value of lock. Now how do you know whether you have the lock or not? If the previous value was 0, then you have the lock because you've just locked it. If the previous value was 1, that means somebody already had the lock and you have not done anything wrong by updating it to 1 because it was already 1. Okay? So test and set is provided as an atomic instruction in most hardware architectures, right? So that enables you to implement locks. Okay, so we'll not get deeper into test and set. It's just important for you to know that this instruction exists in most architectures and it can be used to implement locks, right? So using that I can implement this lock and I can implement critical sections. Okay? So now I've ensured that the updation of sum happens in a critical section. If one thread is executing this set of instructions which together are updating sum, no other thread can at this point of time be executing any of these instructions. It cannot be updating sum. This is the only place where I'm updating sum. So no other thread is touching sum at this point in time. Okay? So I run this code. I got the correct answer. What happened to the time? 671 seconds. You have to be very careful when you write parallel programs. The code that the compiler introduces around a critical section, where the critical section starts and where it ends, is very, very heavy. Okay? Alright, so yeah, this is just a comparison, right? I thought I got it down to 4 seconds, suddenly it's gone up to 671 seconds when I got it correct. How do I fix this? So this is how you do it. Why should they be updating the same sum? Sum is a commutative and associative operation, right? Why can't each thread compute the sum of its own part in a private variable, and in the end I'll update the shared variable? And that's precisely what I'm doing over here, right? So there's a local variable psum, that's a private sum. I add ai to the private sum, and I don't need to put that in OMP critical. I don't need to put that in a critical section. right? There's no race condition over here. The threads are not accessing each other's variables, no shared variables, right? And then when I'm done with this entire loop that I was supposed to work on, at the end, just before exiting the parallel region, I have to synchronize to add up the partial sums. So here I do hash pragma OMP critical and I add psum to sum. How many calls was I making to critical section hash pragma OMP critical? How many times was that being invoked in the earlier code? 1 billion times. How many times is it being invoked now? 4 times. Okay? Finally, I got the time down. 3.56 seconds, and my answer is correct. So I've finally been able to write a parallel program which actually gives me benefits. When I compare it to all the other codes, I'm doing quite well. I have achieved what I wanted to do.